we can now state where the function is increasing and decreasing. Function is decreasing on negative infinity to 0 and 0 to 1. I cannot just say negative infinity all the way to 1. It's decreasing here and decreasing here, but at 0, it's doing nothing because the function doesn't exist there. So I cannot include 0 in this one giant interval. I must pluck it out and have two separate intervals here describing where this function is decreasing. Okay? Function is increasing on 1 to infinity. Okay? Basically everywhere else. All right. So that should lead us almost immediately to part B, where it asks us about local extrema. Find the local extrema of the function. Now, the hard work's already done, right? The first derivative test is practically complete. So local extrema, I just need to find a change of sign where the function exists. Well, there's no change of sign here, but even if there was, it would not matter because we know there's nothing happening at 0 because it was never in the function domain in the first place. So even if there was a change of sign here, we would never say anything about a relative extremum happening there. We're going to ignore this altogether. But over here at 1, we can see that there is a change of sign in the first derivative. So therefore, the function went from decreasing to increasing here. And that implies there must have been a relative minimum. Okay? So we have a local minimum at 1 comma something. Okay? So we just need to plug the 1 back into the original function. So let's look back what that was. It was e to the x on x. If I plug 1 in, f of 1 is certainly just e to the first over 1, which is e. So the local minimum is happening at e. All right, great. So part B is taken care of. Part C, intervals of concavity. Concave up and concave down. So for this, we'll need the second derivative. So, and we apply basically the same test we just did, but through the lens of the second derivative. So f double prime of x should be, what? If we look back, we'll have, here is our first derivative in its most simplified form. We will use this to find the second derivative. So it's again a quotient rule. Okay? I'm going to write the first derivative down here just so we can look at it. X was e to the x times x minus 1 over x squared. Okay, moving through a quotient rule again, we'll have bottom times the derivative of the top. The derivative of the top is a product rule, so I'll have first times the derivative of the second, which is just 1, plus second, which is x minus 1, times the derivative of the first, minus, as part of the quotient rule, top derivative of bottom. So e to the x times x minus 1 times 2x. All over the bottom squared. So that's a square which is squared, so that's x to the 4th. Okay. Now we just need to clean this up as much as possible. So f double prime of x should be, let's see what we have. Go ahead and take out, it's not so obvious, but there's a factor of e to the x sitting in here. I'm going to remove that and get rid of some of these brackets at first. So I'll have x squared. If I take e to the x from here, I have e to the x. Left inside the bracket, right? If I take e to the x out of here to the outside, I would have 1 plus x minus 1, which will end up just being x in a second, minus this should be the same expression it has right here. Really, there's not much of a change. I'm just going to write it in different order. All right, 2x, x minus 1, e to the x, all over x to the fourth. Okay, so this is really just x sitting here. So let's go ahead and write this as x cubed. Have x cubed e to the x minus 2x, x minus 1, e to the x on x to the fourth. Okay, we can factor a little bit further, and we'll take an x out and e to the x out of the numerator. So we'll have x e to the x. We have left, we'll have x squared left on the first term. We'll have 2x minus 1 left on the second term. We can now cancel the x on the outside with the x to the fourth on the bottom, and that will give us e to the x times x squared minus 2x plus 2 all over x cubed. Right, so that's about as nice looking as it gets.